Hi, good evening. Can you all hear me?
Good evening, yes.
Okay, I hope I'm audible to you all. Can you all hear me? I didn't get response from others.
Yes.
Right. Great. So today we are going to see the reaction kinetics topic. Before going to this topic, any doubt or anything, any clarification or any doubt? Okay. Okay, if not, let's proceed to the class, which is a reaction kinetics. Okay, this is talking about the reaction rate, the change in the concentration of reactant or a product with the time. So for example, if you have a reactant A and then it's a B is a product, then the reaction rate is nothing but change in number of moles of B divided by change in time. That means delta B by delta T. So if you want to put it in a reaction rate in terms of reactant, then minus delta A divided by delta T. That's a change in time. So same way for this kind of chemical reaction. That means you have A plus B. These two are reactant and these two are product. And this is the rate. Minus A divided by A into delta T, then minus B. That's a change in number of moles. Right. So the reaction rate and law expression relates the rate of reaction to the concentration of reactant. Okay. Each concentration is expressed with an order. The rate constant converts the concentration expression into the mole per second. Right? That's a general unit. So let's say the reaction rate is nothing but this is a rate constant. If this kind of reaction, more change in mole to the power of m, change in mole to the power of n. This m and n are not stoichiometric coefficient. So this has been determined in terms of experiment wise, it has been determined. For example, for first order reactions, first order process where reactant A gives reactant B. So whenever the concentration of reactant falls off exponentially like this. So initial concentration, that means time equal to 0, that is A naught. Then at any time we can calculate. That's a change in concentration of A, which is equal to A naught into e power minus KT. K is your reactant rate of reaction constant, rate constant, and A naught is your initial concentration. A is a particular time. So then ln A is nothing but ln A naught minus KT. Similarly, you can derive it for a second order reaction. The rate is nothing but K into A squared, this kind of 2A. No? This is a second order reaction. So for then you have an equation which is 1 by A KT plus 1 by mole of A naught. So this is for second order reaction. So from the unit itself, we can say whether it is a first order or second order. For zero order, it is a mole per second. For first order, it is a second power minus 1. For the second order, m mole minus 1, second minus 1. Right? For second order, whether it is a from the
Hello? We cannot hear you. I think the voice interrupted. Hello?
Yeah, I think internet connection.
Some problem.
so then the change in concentration A divided by T, which is nothing but minus K1 FA plus K1 RB. So this derivation you no need to remember, just for your knowledge purpose, how the rate of change is related to the concentration of a reactant. If it is a consecutive reaction, that means A gives B, B gives C. Then we can say A plus B plus C, which is equal to A naught. So the overall order of reaction is a sum of individual orders. For example, if I have any reaction rate with the Ka, then you can add up together, you will get a overall rate of reaction. Then there is a half-life period calculation. Half-life is the time taken for the concentration of reactant to drop to half of its original value. For example, first order reaction, you can say A equal to A naught by 2. That means here, if you substitute here T equal to T and off, then which is nothing but Ln2 by K. It is nothing but 0.693 divided by K. That's a for first order reaction. Similarly, you can derive for second order, it is T and off equal to 1 by K A naught, and then A equal to A naught by 2. That's a half-life. This is the equation. 1 by A equal to KT plus 1 by A naught. If it is a zeroth order, T and off equal to A naught divided by 2K. So this is half-life period calculation is important. And then A versus A naught. This is important for first order and the second order. These all derived from the equation, the rate constant, right? How it is being calculated. This is based on the Arrhenius equation. So that depends upon the temperature. Rate constant is depends upon the temperature. So K is a function of temperature. So it's directly proportional to E to the power of function of temperature. So Arrhenius equation says K equal to AE to the power of minus EA divided by RT. E is your activation energy, and R is your ideal gas constant, 8.314 joule per kilomole, kg mole, I would say, temperature in Kelvin. And A is the exponential order, exponential factor. For both A and the activation energy are specific to a given reaction. Remember this Arrhenius equation. From the Arrhenius equation, rate constant can be calculated. AE to the power of minus EA by RT. So now we go with the CSTR, right? Continuous state tank reactor. So if it is a continuous state tank reactor, means you have a the input, then continuously there will be output. So input minus output, which is if you have any accumulation, I would say minus accumulation, that gives the product. So then you can calculate if it is a steady state, there is no accumulation. So that's a FAI is nothing but input molar flow rate. CA is a concentration of A naught is the initial concentration of A, and CA is at particular time, what is the concentration of A. X is the percentage of conversion, capital V is your volume of tank, small v is your volumetric flow rate. So when related to FAI, molar flow rate is nothing but concentration multiplied by the volumetric flow rate. Right? That's a concentration of A multiplied by the volumetric flow rate, that gives your input molar flow rate. So that's what here, input molar flow rate in and out, then the reaction, which is the rate of reaction, multiply the volume of tank. Right? So when you solve this equation, you will get a V, the volume of tank equal to FAI minus FA naught divided by RA minus RA. So thus, if you derive it, you will get this formula. So when you substitute whatever in the red color, please remember, because you in your exam you're not going to derive, just to remember the formula, that is important. Volume of tank related to the equal to XA. XA is a percentage of conversion. CAI is a concentration of a component A. Small v is your volumetric flow rate divided by RA. RA is your rate of reaction. If it is a first order reaction, RA is nothing but KCA naught. K is your rate constant, CA naught your initial concentration. Remember always CA naught is nothing but at particular time CI minus multiplied by 1 minus XA. So we can substitute this one into here, right? XCAI V. V is nothing but you can put V by V, right? That's a V, you go there. Then it's a KCNR, which is nothing but KCI by into 1 minus XA. So this V by capital V by small v. Capital V is a volume of tank, small v is your volumetric flow rate. That's called a damn hole number, that's called a tau. Right? The tau is nothing but capital V by small v, which is nothing but XA divided by K into 1 minus XA. XA is nothing but the percentage of conversion. You can see here, percentage of conversion. If I know the percentage of conversion, then if I know the rate constant, I can either volume of tank or volumetric flow rate, you can calculate. The same thing, you can write it in terms of damn hole number. Generally, the damn hole number, which is a DA, they say reaction rate divided by molar flow rate. So which is nothing but tau into K. So when you substitute tau into K, the percentage of conversion XA, you can calculate in terms of dA divided by 1 plus dA. So that is from here, XA is nothing but tau K divided by 1 plus K tau. Tau is nothing but capital V by small v. Capital V is your volume of tank. Small v is your volumetric flow rate. So whatever I put it in a red color, please remember that one. The Damhole number formula, the tau formula, then from there how you can calculate the percentage of conversion. Second order reaction is for second order reaction and for batch CSTR. This is for continuous 2 CSTR in series. If it is a 2 CSTR in parallel. Let's take one example of calculation. The activation energy of a first order reaction is 50.2 kilojoule per mole at 25 degrees centigrade. What temperature will the rate constant double? The question EA it is given and the temperature is given. What temperature will the rate constant is double? Rate constant means K should be double. So take here K2, there is a K2 equal to 2K, K1 because the rate constant is double, right? So you take it K2 equal to 2K1. So then when you take it to reaction rate, which is from Arrhenius equation, if you see here, this Arrhenius equation, you can, here. So K1, EA, there is a different temperature R1, right? Then you can K1 and K2. So if you take it to K1 and K2, so here EA by R, which is nothing but 1 by T1 minus 1 by T2. So because EA will be cancelled, you take it Ln. So we know EA value, R value, and the temperature. Remember, temperature always you have to take into Kelvin. So that you take it as a 291 Kelvin. What is given here to 25 degrees. So when you substitute, you can calculate the temperature T2. You can calculate. That is nothing but the answer is 308 K. Can you somebody can calculate and verify whether it is coming? K equal to AE to the power of minus EA by RT. So for K1 you can write 1, K2 you can write 2, like temperature 1 and temperature 2. Then when you divide these two equations, then you will get a ln K2 by K1 equal to EA by R into 1 by T1 minus 1 by T2. From there you can calculate B. Certain reaction proceeds through first order kinetics. So it's a first order reaction. Half-life of reaction is 180 seconds. So T and F is given 180. What percentage of initial concentration remains after 900 seconds? So after 900 seconds, what is the concentration? That's a question. What percentage of initial concentration remains after 900 seconds? The A by A naught they're asking, right? T and F it is given. Yeah, A by A naught is being asked. K is given ln 2 by K. T and F is 180 seconds. So then for first order reaction, T and F is nothing but ln 2 by K. So from there you can calculate K. Where it is saying ln 2 by K, you can go to the first order reaction. What is the T and F formula? You can see for first order reaction, T and F is nothing but ln 2 by K, which is nothing but 0.693 by K. So if I know the T and F is 180 seconds, I can calculate K. So that's how it is being calculated in this question. K is being calculated, which is nothing but 0.000385 per second. Then the question is initial concentration remains after 900 seconds. So A by A naught equal to E power minus KT, where it is saying for first order reaction, you can see this equation, right? A equal to A naught into E power minus KT. So A by A naught is a percentage of composition, E power minus KT. This T is the time, that is a 900 second. This is a 900 seconds. Substitute in this one, you will get a percentage of conversion 3.12%. Is it clear or any doubt? Two questions we have seen. Is there any clear or any doubt? Right. So now we go to the third reaction, which is 2NO-Br gives third question. 2NO-Br gives 2NO plus Br2. That is in a gas, right? It's a second order reaction with respect to NO-Br. K is given because the unit also shows as a second order. They also mentioned second order reaction. The temperature is given as a 10 degree. Initial concentration is given. How much NO-Br will be left after reaction time is 10 minutes. So 10 minutes, after 10 minutes, what is the concentration? That means it's a second order reaction. A they're asking, A naught it is given, K is given. Again, you go back to here, second order reaction. What is the formula for A and A naught? Right? This is the second order reaction. 1 by A equal to KT plus 1 by A naught. A naught is given, A is being asked, T it is given, K is also given, right? Rate constant also given, right? This question, rate constant is given. Rate constant also given. So that formula you can use it. 1 by A equal to KT plus 1 by A naught. So T is 600 second. So the 10 minutes you convert into second. That's the key thing here. 600 second. 10 minutes means 600 second. You need to convert. So when you substitute T is a 600 second. A naught here 7.5 into 10 power minus 3. K is given as a 0.810. Then you can calculate A. A catalytic process for the removal of SO2 from flue gas by reducing SO2 to elemental sulfur using methane has been tested. So there is a catalytic process, two reaction. One is the desired reaction, that's the main reaction. Then there is an undesired reaction. Each rate and activation energy all has given. So what is the question? The question is, in order to enhance the rate of desired forward reaction relative to the undesired side reaction, which of the strategies should be adopted? So you want to reduce the undesired reaction, you want to enhance the rate of forward reaction. So what is the strategy? So first strategy, increase both the reaction temperature and concentration in the feed. Right? That means here, if you increase both the temperature and the concentration, then the both, because here you can see the activation energy. Activation energy depends upon the temperature. So the right answer is here B, increase the reaction temperature and decrease the concentration of SO2 in the feed. That will more favor to the forward reaction. Why? Because by increasing the temperature, the activation energy shows it will favor to more the first reaction, and then by reducing the concentration, so then again it will more forward to the first reaction, the main reaction. If we increase the concentration, it will contribute into both first reaction and undesired reaction also. So first you have to increase the temperature, the first strategy, and also concentration decrease. That will give more favor to the forward reaction. So the right answer is B for this question. Fine. The liquid phase reaction of the first order with the reaction rate constant K. K is given, is carried out in 2 CSTR in series, each with 750 gallon volume. The volume is given, feed rate is given, volumetric feed rate, right? The small v is given. The conversion rate attained by 1 minus 1 plus dA here to the power n. N is nothing but number of tank. So here 2 CSTR, so n is nothing but 2. What is the conversion they're asking, isn't it? Yeah, conversion they're asking. That's a formula also it's given. So we calculate dA and then substitute here, you will get a percentage of conversion. K equal to 0.3 per minute. Volume is given 750 gallon, and this is a 15 feet cube per minute. So that gallon you convert into feet cube. Okay, then you go with the tau calculation. From tau you can dA, the damn whole number you can calculate. So then the formula x minus 1 by 1 plus dA, n equal to 2 here you can substitute. right? So tau dam hole number is nothing but tau k, right? Tau is nothing but capital V, volumetric flow rate divided by the volume divided by the volumetric flow rate. That gives a tau. So tau into k, that gives a dam hole number. From there you can calculate the percentage of conversion. So this is a repeatable question, previously asked question, and this question is a previously asked question. 4 and 5 is being asked. A liquid phase reaction, A gives B with rate constant, K is value is given, batch CSTR with a 500 meter cube value, capital V volume is given, feed rate 40 molar per minute. Here it is a 40 molar per minute, it is a molar flow rate, it is not a volumetric flow rate, which is 70% purity, and the concentration of A is 2 mole per meter cube. That's a C is given, the F is given. The conversion, now they are asking the conversion. K is given, B is given, and feed rate is given as a 40 molar per minute. FAI is given because this is, even though the total is 40 mole, in that 70% is only purity. So FA is nothing but 30 mole per minute. CAI is given 2 mole per meter cube. So what you have to do now, you have to use the CSTR equation, volume, which is nothing but this formula. CAI we know, FAI we know, B you know, then you can calculate the X. This question also is being asked previously. So question number 7, liquid phase reaction A gives B is carried out in a batch CSTR at 77 degrees. The feed rate A is given, molecular flow rate, molar per minute means molecular flow rate is given, concentration is given. What is the volume of CSTR? If the conversion is 70%, activation energy is given, EA is given, temperature is given, K is given, rate constant is given. Same way, this is a more little bit longer calculation. We have to use 2 reactions. Here, what is given, the value, activation energy, all are in 25 degrees centigrade, but we need a rate constant at 77 degrees centigrade. So then you have to use the activation energy formula, ln K2 by K1, which is equal to EA into R1 minus T1 by T2. K1 is given 0.3 per minute. Temperature is given 25 degree. T2 is a 77 degree is given. So from there you calculate K2. Once you know the K2, you can substitute in this equation, right? So calculate, we need to calculate the V, right? So the conversion rate is given as a 0.575. FAI, you know, 10 molar per minute, and concentration we know it's a 2 mole per meter cube. So then K2 you substitute, you can calculate V. So here the 6th question is only talking about the CSTR and calculate the conversion. All are in one temperature, assuming they are not talking about any temperature here. So it's assuming all happening in the one. Here, when you're talking about here, they have given 77 degree, but all the, you need to calculate the rate constant is not given, but rate constant is given into 25 degrees centigrade. When come to the 6th question, they have given the rate constant 0.1 per minute, it is given clearly, but here they have given in a different temperature. So for that only you need to use this K2 by K1 equation, then calculate K2, then substitute in this formula. The decomposition of the question number 8, the decomposition of PCl3 by first order reaction. It is found that concentration of PCl3 is 0.0384 mole after 250 seconds. 0.0150 mole after 400 seconds. What is the rate constant, half-life, and the initial concentration of PCl3? So the decomposition of PCl, it's a first order reaction. So found that concentration of PCl3 when T equal to 250 seconds, concentration is given. When T equal to 400 seconds, concentration given. What is the rate constant, half-life, and A0? We know, right? We have a T1 minus ln A2, which is something but K into delta T. So it's a T and half we need to calculate, which is nothing but ln2 by K. How do you know the K? K you can substitute in this equation. So for example, time is change in time. Say 400 minus 250. That's a 150 second delta t. Then you can take it as your we will say is the t. Okay, 0.0384 minus 0.0150 divided by, you can see the 150 second. That gives your K value. From the K value, you can calculate T end off, right? So once I know the T end off, I can calculate the initial concentration also, right? That's a ln equal A0 minus AT1 to K into delta T. So if we calculate in that manner, the right answer here it is C. So how do I know this is the formula I have to use? If you go to the first order reaction formula, ln A naught, first order reaction. This one, right? ln A minus ln naught, right? That's the equation you have to use. So that's a reaction kinetics. Maybe from reaction kinetics, so far what I understand, one question or two question max you will get. Generally, what all the 8 questions, whatever I shared here, mostly it's a repeatable question. And CSTR related question has come, and that theoretical question, which forward reaction, what is a strategy to really get the forward reaction? So that kind of question is possible. So it's a very little bit small topic.
Hello, madam.
That's it. Yeah.
Madam, can you provide us a list of the all repeatable questions in the all sections? Is it possible?
See, we shared in your frequently asked question in the material.
You are sharing during the training. You just shared a list on the WhatsApp. These are the sections and these are the repeatable questions. Can you do this?
That's what I'm talking about the material what we shared. There is a one slide which is called a frequently asked question. You can see one slide in that material. So all the question in that slide is being previously asked, and I have taken some of the question from the slide with related to the chapter. Then I put it in the chapter. Then I have explained. So the frequently asked the question slide gives all the feedback from the students. Whatever the repeatable question is summarized in that slide.
Okay.
Right. So any more doubt in reaction kinetics? Is a very small topic. Understand about first order, second order, then the initial concentration, T end off, and A1, A0, right? That formula. And then when you go to the CSTR, you remember that the tau formula and V, the V equal to XA FAI divided by KCA, I multiplied by 1 minus XA. That formula all you have to mark up. Then just practice all those questions. That's it. Right?
There is no, sorry, there is no, I remember I have, if I remember correctly, for the thermodynamics, there was a formula to estimate the unit for the K constant. Do we need to know that? What would be the unit? If you know the reaction order, there is a formula, you substitute, and then you will be able to know what would be the unit.
See, this is the unit for rate constant. Right? K first order means from the unit itself, you know whether it is a first order or second order. If based on the unit, you can get the first order or second order.
Saying that if the question is to estimate what would be the unit, if you know the reaction order already, this table must be derived from that equation or formula.
Yeah, but we no need to remember the derivation or equation. By seeing the unit itself, you can see whether it is a first order, and that's what I have given the summary here. Because Your question is only to see the ABCD. It's an MCQ only. So you don't need to remember that equation. If they have given that unit, then you know which order of a reaction it is.
Okay.
Any more question? CSTR in series, CSTR in parallel, and the dam hole number, tau, then T end of, then the A, 1 by A equal to A naught for first order and second order, that formula. We all mostly reaction kinetics, if at all it is being asked, it is a calculation based question. And only one repeatably the theoretical question also is the only one theoretical question is asked. That one. Right. So now we will go to the next chapter, which is the economic analysis. That's the last chapter. Economic analysis will be helpful for to see the feasibility of a project. When talking about the project or any other manufacturing industry, the profitability, what is my total cost, direct cost, that kind of selling price. For those calculation, this economic cost analysis will be performed. The feasibility of the project, then the feasibility of producing a product within the acceptable pricing range. So for this purpose, economic analysis is being conducted. Before we do the proper economic analysis, we should take what are the costs involved. We can see direct cost, material cost, that is all the real cost involved. But when it comes to the economic cost, there are 4 major costs here, to really see which one gives you the more benefit. That's called economic feasibility. So in that, you have to consider 4 economic costs: opportunity cost, sunk cost, book cost, incremental cost. Okay, these are economic costs. Okay, it's not these are not like direct cost, indirect cost, or variable cost. Fixed cost means if the whether the project is progressed or not, whether you are selling the product or not, there are some fixed costs you have to spend. A company have to spend. For example, office rental, or if you have a permanent salary, these all are fixed costs. Variable cost means it varies with the progress. How many material is being used, accordingly the cost will vary. These are the variable costs. So generally, when you do the costing, you will take a direct cost, indirect cost, right? In the direct cost, you'll have a direct fixed cost, direct variable cost. Similarly, the indirect cost also, but sometimes indirect cost will be taken into the percentage. Some percentage they will consider. So these are the direct, indirect, fixed, variable, material cost, labor cost. These are really a costing structure. Here, we are not talking about that cost here. Here, we are talking about the economic cost to really study the economic feasibility. Right? What is opportunity cost? Opportunity cost that represent the foregone benefit by choosing alternative over another. That means I have a 2 alternative. Which one to choose it? It could be a product, or it could be a project, or it could be in your project there is a 2 alternative, right? Which method I have to use, or which equipment I have to use. At that time, you have to think about the opportunity cost when you see the real worth of that particular decision. So that particular decision, if let's say A and B, there is a 2 alternative. If I have selected B, so then I have lost the whatever the opportunity come from the B, right? That I have lost. That cost is called opportunity cost. That also you should include it when you calculate overall the value of B. You cannot just take it about the only cost of B. So you have to see the opportunity cost that you lost it because of the decision by selecting A. That's called opportunity cost. Opportunity cost represent the foregone benefit by choosing one alternative over another. So it can be value of a product foregone to produce or obtain another. For example, in a building the hospital vacant land, the city has foregone the benefit to build some sports center, some parking lot, and everything. Note that opportunity cost is not sum of all alternatives, only the best two you have to consider. Sunk cost. Sunk cost means you have already spent, right? For example, you may have done some kind of what do you call it, about model you have already prepared, or sometime some early part of study you might have done for client. So these are the some kind of, before the project is awarded or for the benefit of getting that order, something you have spent already, right? That's called a sunk cost. That is money you already spend by virtue of the past decisions. So future decisions should not be based on the sunk cost they're telling, but normally you have to consider the sunk cost also in your economic analysis. Book cost. This is the book cost, very, very important, because what is the value of that particular asset or machine or equipment in the company account book, right? That's called asset are carried in form